As explained before, we need a new model to finally explain some of the observations that scientists have been struggling with for decades or even centuries. This model implies some drastic changes in our view of the universe architecture. Let's see what these implications are and the assumptions we need to start from. First, we must remember that we always use electromagnetic waves, or fields, to directly observe and measure physical events and objects. For instance, it is light photons which allow us to see an orange. These photons are constituents of a special case of electromagnetic waves called light. But electromagnetic forces are also what make us feel objects and prevent, for example, a hand from passing through a table. And we can generalize this principle as what allows us to perceive things are always electromagnetic fields. Okay, so we can observe things only thanks to these so-called electromagnetic fields. But what if we want to go further down and observe the entities and processes which create the events that we directly observe as electromagnetic waves? We can't have a direct access to these entities because by definition, they exist beyond electromagnetic waves. So we have to assume there is another domain or other dimensions of the domain we live in where these entities exist and follow rules which eventually yield the events we can observe. Please note the names that we're going to be using for the two domains, the space-time domain and the quantum substratum domain. Now let's have a look at how things work when we see the orange, for example. From a macroscopic perspective, a light wave hits the orange and then seems to bounce back to our eyes. This is what we observe in the space-time domain. Now let's have a closer look to see what is really happening. Please bear in mind that the pictures you are going to see are there to give you a feeling of what's going on, but do not represent objects that can be directly observed as shown, although they're definitely real. Okay, let's study one pixel of the orange skin, and this of course can be generalized to the bunch of pixels which make up the orange image. An atom in the orange is receiving a light photon, which will increase the energy of the atom. Then, according to some decay rate, the atom will release a photon of energy, and the electron will get back to its standard energy level. This photon will be sent to one of our eye's atoms, which in turn will have its energy level updated, and things will continue like this until a transmitted photon reaches an atom of our eye's retina photocells, triggering an electrochemical chain reaction so that we can perceive it. All of this seems to happen in the space-time domain, but the theory I am presenting to you is, well, different. What is really happening, according to this theory, is that the energy received reaches the orange atom in the quantum substratum domain, which then triggers a bunch of interactions in that domain with all the potentially receiving atoms. These interactions will determine the probabilities of reaching each of these atoms. Based on that probability, a stochastic rule applying to that domain will pick one of the candidates. It is that atom which will have its energy level upgraded, and that will create the event that we observe in space-time domain. But again, please note that what created this event happened in the quantum substratum domain, and the resulting event is the combination of the emitting atom event, the receiving atom event, and the photon energy. We'll see in the next videos how this new interpretation can be used to explain so far unexplained behaviors of elements of our universe. It also means that space-time does not exist by itself. In other words, it is not a playground where massive objects and particles travel around, but it is instead defined by the events themselves and updated in real time to be observed by our senses or some lab apparatus, thanks to electromagnetic fields. Now you might wonder why we cannot make a direct observation of these real interactions occurring in the quantum substratum domain. Well, first of all, human being senses can only detect energy changes in their body's atoms. And this applies to machines and lab apparatuses as well. So the only interactions we can directly observe involve an energy transfer, which can be observed as a four-dimension space-time event. The rest of the interactions remain hidden in the quantum substratum dimensions, a little bit like tiny beings who would live in a two-dimension plane. All they could see is what happens in this plane. But say that a three-dimensional sphere passes through the plane they live in. All they would see would be the intersecting line of the 3D sphere with their 2D space, and could derive that it is a circle. And similarly, that's how we perceive in our four-dimension space-time domain the results of the interactions fully occurring in the hidden dimensions of the quantum substratum. Before we look at the implications of this new way of interpreting the laws of the universe, let me summarize the two main characteristics of this new interpretation. The first major difference between this new theory and the standard theory is the existence of another domain where events actually happen, and the fact that it is the events which are actualized via energy transfers which constitutes space-time. But we've also seen the importance of atoms' responses in the interactions. Usually, physicists only focus on the emitting atom to describe how the field, or waves, behave. But as I showed you, the emitting atom initiates interactions with all potential receivers. Actually, this was an idea by legendary physicist Richard Feynman and his brilliant colleague John Wheeler. It was called direct action theory, but it was used for other purposes, and Feynman and Wheeler chose other directions for the immediate problems they wanted to solve. But again, we'll see in the next videos how this interpretation, updated to take into account later developments in physics, will help us answer some of the so far unresolved questions in physics.